Welcome to lesson 47. So now we're going to talk about multiple linear regression, determining the fit of a model. So when we have a quantitative response variable and multiple explanatory variables, determining whether or not the linear model that we fit, whether or not it's a good fit. So we're going to talk about the equation. So multiple linear regression analysis. It models the relationship when we have one quantitative response variable and multiple explanatory variables. So last week what we looked at was one quantitative response, one quantitative explanatory. Now what we're going to do is look at one quantitative response and multiple explanatory. So they can be a mix. You can have quantitative explanatory, categorical explanatory, and or both. So the equation, it's never going to now represent just one single line. It can be multiple lines or a plane. So here, now we're going to have y hat is equal to b naught or b0. So that's our y-intercept plus b1 times x1. So our first slope-intercept times our first explanatory variable times plus b2 times x2, which is our second slope-intercept, our slope coefficient plus our second explanatory variable, all the way through whatever our last explanatory variable is here. So here, we're trying to estimate coefficients for beta naught, beta 1, beta 2, all the way through whatever beta k is. B0, B1, B2, all the way through BK, they're unbiased estimates. So if we were to find, if we were to collect all population data for all individuals in this population and find a population line, if we were to simply take a sample, a random sample, or representative sample from this population, the estimates we get from that sample are unbiased for what that population line would be. And then y hat, it is absolutely very important to include the hat. It's the average response given some specific set of explanatory variable values. So absolutely, it's going to be very, very similar to last week, where those variable coefficients, we calculate them by using sum of squared values. So sum of squared error versus sum of squared model. Absolutely very, very important here. So multivariate regression equation, the example that we're going to use throughout this particular set of lessons, we are going to look at the Nintendo Wii game, Mario Kart, which either you love or you hate, or you don't know what it is. So we're going to go ahead, we take a random sample of 141 auction sales for this particular game. We're interested in modeling what the total sale price, so what it sells for. So this is some video game, we want to know what it sells for, but we're going to base it on a few different factors. We're going to base it on what the starting price is. So the way eBay works is there's a starting price and people can place bids, which leads to our total price, what it ends up selling for. We're going to factor in the number of Wii wheels included. So this is a little old school, but back then in the day, the Wii came with Wii wheels, or certain games did. And then whether or not the game was used. So we want to factor in what the starting price was, the number of wheels that were included, and whether or not the game was used. And here, just to make it very clear, I have it very well defined here that X1 is the starting price of the bid, so that's going to be in US dollars. I have X2 here, it's going to be the number of Wii wheels included. X3 is going to be the condition. So in this case, this is what we're going to go into later on as an indicator variable. It will be assigned as 0 if it's new and a 1 if it's used. So using our software, we go ahead, we get this output here. We get that here's our y-intercept, so it's about 41.8 plus 0.12, and I rounded to 2 places here since everything was in dollars, times the price of the starting bid, plus 6.63 times the number of wheels minus 5.69 if times whether or not it's used. So once again, if it's brand new, you're going to plug in the 0 for X3. If it's used, you're going to plug in a 1. So the software output is going to look identical to, well, or at least very similar to what we saw last week. The main thing is, so here we had beta naught, beta 1, but now we have a beta 2, we have a beta 3. We have more rows. That is essentially the key difference here. But now that we've fit a model, we want to know, is this a good fit? Is this going to be a reliable model that I can go ahead and plug in scenarios here and it will make a reliable prediction for me? So one thing that we'll use is the coefficient determination R squared. So here, R squared, it's going to look at the sum of squares from our model, or sum of squares regression, over our sum of squares total. So like how much variability is explained by the model over all of the variability that there is to explain. So that will tell me, okay, well, this percent of all the variability there is to explain is explained by the model. That kind of idea. The higher it is, the better. It can go anywhere from 0 to 1. So here, you can also rewrite it as 1 minus the sum of squares error over your sum of squares total. So absolutely, this can be used to compare fits between models. The closer to 1, the better that the fit is going to be. Just keep in mind, it will matter how many variables you have in your model as well. So here's sum of squares total. This should be very similar from week 8. So the total variability. So here you're looking at every single individual value in the response. How far is it from the overall mean? That will be your total variability of y. And then your regression sum of squares. So this is how much sum of squares your model explains. So it looks at variation between the predicted variables and the average responses. And then this is left over, the error. So the error sum of squares. So what's left unexplained by the model. So we have what's explained by the model plus what's not explained by the model. Oops. What we get is all of the variability there is to explain. So looking here, Mario Kart model, we have a sum of squares regression of 8,810.4 and sum of squares error 2,817.8. We want to know what percent of variation does starting price, number of game wheels, and condition explain in total selling price. So here, what we want to do, we want to look at what's R squared. So R squared is going to be what's explained by the model over everything there is to explain. So notice here we didn't quite give you sum of squares total, but we did give you enough information to calculate it. So here it's going to be 8,810.4 over total. So that 8,810.4 plus the 2,017.8. So here, looking here, because this is not math in my head, 8,810.4 over 11,628.2. So as you can see, just 8,800-ish over 11,600 or so. That's a lot of it. I'm going to get 0.7577. This is a proportion. So if I thought of it as a percent, roughly 75.77%, which is right here, of the variability that there is is explained by the starting price, number of wheels, and condition. Is explained by the regression or the model. So now that we are interpreting it here, absolutely it's very related to thinking of the correlation coefficient. But here we have multiple variables. So the higher the R-squared value, this means the better that our model is at explaining the variability in the response. Basically, the better your model explains the variability in the response, the better you are at predicting what's going on with the response variable based on what explanatory variables you have. So here, if it's at 0, this is saying your model is horrible. You know, the explanatory variables that your model has does not help explain what's going on in the response variable at all. All the way to a 1. If you have an R-squared of 1, that means your model explains everything that's going on. Usually this is a bit idealistic. 1 is a bit high. Honestly, we'd love to aim for, like, good to very good. Perfect is less likely. So, looking at our model here, we're going to go ahead here. We're going to take for starters here, our multiple R-squared, and we'll talk about what adjusted R-squared is later. We will use this later, just not yet. So, based on our multiple R-squared, the explanatory variables in the model explain 75.77% of the variation in the total selling price for the Mario Kart on eBay auctions. So our R-squared is 0.7577. And based on that, now I'm looking here, it looks like it's a very good fit. I would say that using starting price, the number of wheels included in the set, and whether or not it's used is very good at explaining what the selling price is. So looking at interpreting R-squared and adjusted, so I hinted at this in the last slide. So cautions about interpreting R-squared. So it depends on what field you're in, how comfortable people are looking at R-squared versus the adjusted R-squared. Because the R-squared doesn't account for how many variables you include, the adjusted R-squared does. So here, if you include 2 explanatory variables that are related to one another, it can inflate the R-squared. Definitely it's problematic because if you just add explanatory variables to the model, it can force your R-squared higher and higher. However, the adjusted R-squared takes into account how many variables you're including in your model. So there's almost a penalty. Like if you include too many explanatory variables, that matters. The unadjusted, it does not take into account how many variables you have. So adjusted R-squared accounts for the number of variables. So it can adjust for overfitting. So that might be the scenario where maybe I only have 10 observations. It would really be problematic for me to go ahead and add 9 explanatory variables. That would be really problematic. So you want to account, you almost want to have a penalty for adding too many explanatory variables to your model. So you're adjusted here, it's 1 minus, and then you have this this adjustment here. So you're absolutely, K is the number of parameters you're adding here. It's accounting for how many variables you add to your model. So here, we're returning to our GPA example. So we want to compare the fits of the model that predicts college GPA. One of them had just high school GPA, and one of them had high school GPA and SAT. And based on what we see, we want to know, well, which one is a better fit? So here is our model with SAT and high school GPA, so it has both. So you will have slightly fewer degrees of freedom. So 7 degrees of freedom as opposed to 8. And then from there, you're going to look at, well, what is my multiple r squared? So 0.682. So about 68.21% of the variability in college GPA is explained by SAT and high school GPA. Versus if I only have high school GPA, 66.73% is explained by just high school GPA. There's not a huge difference here adding SAT in there. Adding SAT in there does not explain a whole lot more, which is probably why we'd say, you know what, maybe it might be better to go with only using high school GPA. One consideration too is high school GPA is also very related to the SAT score. Absolutely. Okay, so let's go ahead and compare the adjusted r squared to the unadjusted r squared in the output for the Mario Kart example. So looking here, we have our output. This is what you'd use to go ahead and put the linear model together. Multiple r squared, so we're looking at this row, is 0.7577. Adjusted, so when I do account for the number of variables I'm including, it explains about 75.24% of the variation in the total selling price, including these 3 variables here. Not only that, accounting for the fact that I have 3 variables. So 75.24%, that's a pretty good fit. I would say that's a very good fit based on the spectrum we saw earlier. Absolutely. And one thing that's nice is the unadjusted 0.7577 and the adjusted is 0.7524. They are very similar. When they're very similar, this is great. When they're not very similar, we tend to go with the adjusted. That tends to be the safer bet because the adjusted goes ahead and adjusts for the number of variables you've included to your model. So that's it for lesson 47. Then we're going to talk about the model utility F-test.